Hello everyone, we're discussing atomic structure and we have developed energy when electron is in the nth orbit, and this was minus of 13.6 z square n square electron volts. This is the energy of an electron when it is present in the nth orbit. Now I'll ask you a very elementary question. So if we show the energies in this form, N1, N2, N3. So as you increase N, what happens? Total energy of electron increases or decreases? Write down fast in the comment box. As we increase N for a given Z, then what happens to the energy part? Does it increase or decrease? Try to answer this elementary thing fast in the comment box. Good. As you increase N, denominator is going to increase, numerical value will decrease, but since you have a negative sign, overall energy is going to increase. For N equals to 1 and for hydrogen, this is minus of 13.6 electron volts. N is 1 and Z is also 1. For this, 13.6 divided by 2 square. For this, 13.6 divided by 3 square electron volt. Now, tell me, if an electron jumps from n equals to 2 to n equals to 1, if you have an electron in the second orbit with principal quantum number 2 and jumps into n equals to 1, then the question is, you are jumping from high energy to a low energy orbit, and in the process this thing will release some energy, and as that energy comes out in terms of electromagnetic radiation, we need to find its wavelength. So I'm asking lambda when jump is from 2 to 1. Present your answer in terms of H, C, all these things. You don't have to put values of H and all. So get me the value of lambda when jump takes place from 2 to 1. Put on this. When you're taking too long. If you are jumping from 2 to 1, then energy released is what? E2 minus E1. And this energy then is lost in the form of electromagnetic radiation, whose energy is given by Hc upon lambda. E2 minus E1 is coming what? Hc upon lambda. E2 is minus of 13.6 divided by 4. E1 is minus of 13.6. This gives us 13.6 minus minus plus 13.6 common, 1 minus 1 by 4. That is 13.6 into 3 by 4. This is your HC upon lambda, and the value of lambda from this is coming HC multiplied by 4 divided by 13.6 into 3. That's how we can find wavelength. Now, I'm just asking you a question. Maybe you have the idea of this thing. Can you tell me which hydrogen spectrum series we are talking about when I say that electron jumps from 2 to 1? If you have already seen these things in chemistry, in physics, anywhere, if you have the general idea of all these things, then can you tell me which series are we talking about when we go for jumps from higher energy orbits into n equals to 1? Note down this and try to answer the question. Good. We are talking about Lyman series of the hydrogen spectrum, and this is the first wavelength. If we go for jump from 3 to 1, you will get lambda 3 to 1. Replace this 4 with 9 and you can find the wavelength. Now, the second question, again, do you have the idea of the profile of Lyman series? Does it lie in visible range, infrared, ultraviolet? Again, something which you can expect in any examination. And I'm just asking you if you have the idea of all these things. So what is the profile of Lyman series? Does it lie in infrared, visible range, or ultraviolet? Well, one of you have answered correctly. Lyman series lies in ultraviolet region. Over here, ultraviolet. That's what is your Lyman series. It fits right here. Go down this way. And let's see how many of you will answer the second part. Write down the question. A hydrogen atom is at rest. A hydrogen atom is at rest. An electron jumps from An electron jumps from n equals to 3 to n equals to 1. An electron jumps from n equals to 3 to n equals to 1. Afterwards, find out linear momentum of the hydrogen atom. Afterwards, find out linear momentum of the hydrogen atom. Let's see if we can answer this question. Well, no response. Let me give you the hint. Take the hint. As electron jumps from n equals to 3 to n equals to 1, a photon comes out. And if photon comes out, then it has what? Linear momentum. So if photon has a linear momentum, then from COLM, conservation of linear momentum, since your atom initially was at rest, something is coming out with some linear momentum, and then to conserve overall linear momentum, atom should move back in the opposite direction with same amount of linear momentum, magnitude wise. So basically I'm asking you linear momentum of the photon. If you can find linear momentum of the photon, then with same amount in the opposite direction, your atom will move. Let's see if you can answer the question now. Look, if jump is from 3 to 1, then this will become E3 minus E1. This will become 9. This will become 8 by 9. So what is 13.6 into 8 by 9? Hc upon lambda. But what is de Bro's hypothesis? De Bro says that linear momentum is h upon lambda. That's what is de Bro's hypothesis. So basically I'm asking you h upon lambda. I'm asking you this, h upon lambda. So what is the value of h upon lambda? 13.6 into 8 divided by 9 divided by c. That's your h upon lambda. This is linear momentum of the photon. Let's say this is the atom and this is the photon. Photon is moving in this direction with p. Atom is moving in this direction with minus of p. So that overall linear momentum remains what? Conserved. So instead of asking you lambda, I asked you what? H upon lambda. And nobody could answer this correctly. But I hope situation is clear now. This is the hydrogen atom. This is the photon. Put down this. The next series in hydrogen spectrum is Balmer series. This time jump takes place from N3 to N2, N4 to N2. That's how these jumps will take place. This one is lambda 3-2. This is lambda 4-2. We also give them special names like lambda alpha, lambda beta, lambda gamma. So when I say lambda alpha, remember jump is from 3 to 2. When I say lambda beta, jump is from 4 to 2, and so on. Instead of a big jump like this or like this, you're getting smaller jumps. So since you're getting smaller jumps, energy of photon will also decrease. So the Lyman series was in Lyman series was in ultraviolet, beyond violet, more energy. The Balmer series, it lies in visible region. In fact, just for your knowledge, first 4 lines they are between 4,000 angstroms to 7,000 angstrom range. First 4 lines. 1, 2, 3, 4. First 4, they lie in the range of Wave-Georg, that is from 4,000 to 7,000. That is enough for us to remember. And to find lambda, the only thing you need to do is what? Or tell me, this is alpha, this is beta. I'm asking you value of lambda gamma. Suppose question comes at find out wavelength of photon for Balmer series where wavelength corresponds to gamma type. What are these alpha, beta, gamma? They simply tell you these jumps. Let's see if we can answer this part. Everything is same as you did in the first one and therefore should not take more than 40-50 seconds. Try to answer this. Are you taking too long? Energy of the photon hc upon lambda gamma. Gamma means we are interested in this one. Jump is from n equals to 5 to n equals 2. So you'll be writing E5 minus E2. E5 minus E2, which is HC upon lambda. Take minus of 13.6 out, 1 upon 5 square E5, Z square upon N square, Z is 1, minus 1 upon 2 square. That's how you can find lambda. Well, if you did something like this, then write down yes in the comment box. If you could not solve for it, but if you have done the same thing, then write down yes in the comment box. The next series, just remember, is the Paustian series. And jump is into n equals to 3. This is the jump. This will be lambda alpha for Paustian series. Alpha stands for the first one. First means first jump is from 4 to 3. So for Paustian series, lambda alpha will be lambda from 4 to 3. Now, can you answer this? The first one was in ultraviolet region. This one, Balmer, is in visible region. What about Paustian series? In which region Paustian series is going to lie? Answer this fast. In red, you see Paustian series lambda alpha. This is not lambda alpha, my fault. This is lambda beta. The jump is into, this is your lambda beta, which I have shown you. Lambda beta. When jump is from 4 to 3. This will be your lambda alpha. Good. Paustian series lies in what? Before R. That means what? Infrared. This Paustian series, it lies in infrared region. Write down this way in a separate figure or the same thing, and then write down that Paustian series wavelengths, they lie in the infrared region. Next series is bracket series. For bracket, first tell me jump so that you get lambda beta. In the comment box, for what jump you will get second spectral line of bracket series. Follow the same sequence and then also find out lambda beta. Please do not disappoint me. At least try to answer this one. Good. Some of you answered correctly. Lyman, Balmer, Paschen, bracket. This is lambda alpha. This is lambda beta. So lambda beta means jump is from 6 to 4. This is the second spectral line for bracket series. Now find out value of lambda beta. HC upon lambda E6 minus E4. If you can write like this, that this lambda is 6 to 4. Follow this sequence 6 to 4, 6 minus 4, 6 is square minus 4 is square. And you have found the wavelength. Note down this. Well, the energy of bracket series is even higher than the infrared. You can write the statement. Energy of bracket series wavelengths is higher than the what am I saying? Tell me, is it higher or the energy will be lower? Answer fast. I said that energy of the bracket series, it will be the term which I use, that energy will be greater than the infrared. So, is it correct to say that energy will be greater than the infrared? And I hope anybody is saying no, because this is your Vidgear. As you move in this direction, energy increases. This was infrared. Your bracket lies over here. Which is also called far infrared. This type of region is also called far infrared. You don't have to worry about this far infrared, but remember, as you move in this direction, energy is going to decrease. It's also very obvious, if you take a jump from this position to this position, or you take a jump from this position to this position, you can see that this is a much smaller jump, and therefore energy release will also decrease. So this is far infrared region, but energy is decreasing. The next one is Freund series. I hope everybody knows about that. It's a simple repetition of all these parts, and therefore without taking much of the time, get me lambda, gamma. When I say get me lambda, gamma, first tell me jump for which you will get lambda, gamma of the Freund series, and then find its value. For what jump you will get lambda, gamma, and then its value. This is the last profile of this type, and therefore try to answer this thing correctly. Oh, bracket series doesn't lie in infrared region. It is beyond, over this side, in the far infrared region. Sometimes people can call it infrared, but remember, it lies in the far infrared region, which is even much lower in terms of energy. So if you are talking about Freund series, then jump is into fifth one. This will be lambda alpha. The first spectral line from 6 to 5. Second will be 7 to 5. Third, which is the gamma, is from 8 to 5. And then you know what to do. If it's from 8 to 5, just write down 8 to 5, 8 to 5, 8 square, 5 square, and you can easily calculate its value. Just draw a setup like this, and you can always figure out the type of jump we are interested in. This is 7, this is 8, this is lambda beta for the Freund series, this is your lambda gamma. Third spectral line. Write down this. Now we have found all these wavelengths using Bohr's model, but even before Bohr tried to explain all these things, Rydberg found that all these wavelengths of all these series, they satisfy this relation, some constant which is called Rydberg's constant, one upon m, and let me use m over here for simplicity. Whenever you make a jump from n to m, you can write like this. Just for your simplicity, you can always write n1, n2, you can always write n dash, whatever you wish. Let's use nm. So what Rydberg found, that whenever these jumps they take place, these jumps always satisfy this type of relation. So he just found mathematically a particular pattern and then empirical value of the constant. Now we need to find value of r using Bohr's model. Remember, we have found E6, E4, these type of things. What I expect from you, value of lambda, value of Rydberg's constant when jump takes place. First tell me this jump is from n to m or m to n. Jump is from n to m or m to n. R is a positive constant. Write down fast. If I write something like this, just show me your activeness. The jump is from n to m or m to n. R is a positive constant. Now hopefully you're not writing jump is from 6 to 4. 6 to 4. Why? Because look at the sign. Negative part. If I say R is positive, then jump is from m to n. So in this case, jump is from m to n. That means m is greater than n. When n is 1, you get the first spectral line of Lyman series and so on. Now, in terms of Planck's constant, speed of light, charge, permittivity, everything, you can see your notes, the way we develop the whole format of energy. The term 13.6, what it was basically. So I'm asking you R in terms of these fundamental values. Take 1 minute's time, note down this much, and then get to the value of R. Look here. Just see your notes and find out En. It was minus of 13.6 z square upon n square. The basic version is basically z square, Rydberg's constant, 1 upon n square minus 1 upon m square. For hydrogen, this value of Z, for hydrogen, Z is 1, and therefore you get this. So, En we have found minus 13.6 Z square upon n square. What I am saying is, see your notes, or if you can figure out yourself, then what this 13.6 was basically. I'm asking R Rydberg's constant in terms of all these things: mass of electron, charge of electron, Planck's constant, permittivity. If you remember the terms like K, Q1, Q2 upon R square, 1 upon 4 pi epsilon 0. Take another minute and then get me the value of Rydberg's constant. Rydberg's constant using Bohr's model. We have done all these things and therefore I'll be fast. Electron, proton, nth orbit. Force. The force part gives us mv square upon r. K times q1 q2 upon r square. You're talking about z equals to 1. Very easy to remember result: mv square upon r, k square upon r square. Energy in nth orbit. What is the energy? K plus P. K is half mv square. Look here. What is half mv square? Half mv square is k square upon r. This was k e square upon r. Half mv square. Potential energy is what? K e square upon, this also has a term of, so if I write half, need to add 1 by 2. This was giving you minus of k square upon 2r. Energy. This is energy in terms of r, but you know how to convert this r in n, in terms of n. Once you convert r in terms of n, you can answer the question. So I hope you remember all these steps. I still see no correct value. I don't know if you has presented. It looks good. Taking too long. MVR. It is NH upon 2 pi. We need R in terms of N. That's your MVR NH upon 2 pi. And after this, we do this M square V square M square V square R square is n square h square upon 4 pi square. Square these things. Divide. So when you divide, terms of v square and v square are gone. That's why we did this. So once the terms of v square are gone, you can find r in terms of n. You can use any other method. You have the value of v in terms of r, put it here, and you get r in terms of n. I've simply squared the whole thing so that I can cancel v square and v square, m n square. This is r square. Look carefully. This is r square. This is 1 upon r square. This r square and this r square, they are cancelled. This and this, they are cancelled. So you get 1 upon r, 1 upon r, and the term of m. Right there, it's k e square upon n square h square 4 pi square. So the value of 1 upon r is now available to us. One upon r is coming m times e square k 4 pi square upon n square h square. Minus k square upon 2 is already present. 1 upon r is m times k square into 4 pi square n square h square. So this term, which was 13.6, and the z is 1, remember. So this 13.6 is basically what? The term 13.6 is k square e to the power 4. K square e to the power 4 m pi square upon h square 2 and 4 2 times. I think all the terms are present. K square e to the power 4 m is there, pi square is there, divided by h square followed by 1 upon n square. So this is, when you convert in electron volts, gives us what? 13.6. So as of now, this is the constant we are interested in. So wherever we are writing that minus of 13.6 type of thing, we are doing basically E of the photon. What is E of the photon? Hc upon lambda. That is energy of the photon. Energy of the photon jump is from m to n. In this format, jump is from m to n. So you'll be writing energy of the high energy orbit minus energy of the low energy orbit. That is Em minus En. So once you write Em minus En, this becomes, right here, this is giving us Hc upon lambda Em, the whole thing, minus of this constant. For the time being, let's call this constant A. This whole thing, let's call it A just for the time being. So this is minus of A divided by n square. So this is minus of A divided by m square minus of A divided by n square. That is A times 1 upon n square m square and then 1 upon lambda. 1 upon lambda is R times 1 upon lambda is what? A divided by HC. If I need 1 upon lambda, then that is what? A divided by HC. So the Rydberg constant R is A divided by HC. What is A? This is A. Divide the whole thing by HC and your answer finally becomes over here. Your R is coming 2 k square e to the power 4 m pi r square divided by h square cube c. So Rydberg found the whole thing using all the experimental results. But then Bohr tells us that you can find Rydberg constant using all these very fundamental values. Replace k with 1 upon 4 pi epsilon 0 and you can further refine the whole thing. Note down this much and rest we'll discuss in the next class. Before you go, unit of Rydberg constant. What is the unit of Rydberg constant? R, number, lambda, meter, 1 upon meter. So unit is meter inverse. This m is mass. This is the unit part. What is the unit? 1 upon meter or meter inverse. N number, R, even along with Z is also a number. So unit is coming what? 1 upon meters. Put down this and then you can leave. Thank you.